You know when you look at a brilliantly tiled floor or maybe a really intricate carved stone border on an old building, and you just kind of wonder, what are the hidden rules actually governing this design? Well, hello everyone, and welcome back to The Explainer. Today we're diving into a really dynamic investigation of the hidden architecture of our visual world. We're going to look at exactly how mathematicians use visual symmetry not just to build rules, but to strategically break them. So if you're the kind of person who loves seeing how complex, abstract ideas can be broken down into super clear visual structures, you are absolutely in the right place. Let's get into it. So think about this. What actually happens when infinite mathematical symmetry crashes into a relatively simple geometric shape? Well, you get an intricately repeating, infinitely stretching pattern. And this right here is the central mystery of our explainer today. How do we get from a single, simple shape, maybe even an ugly, totally asymmetrical one, to a gorgeous, infinitely repeating pattern that you might find in architecture or even out in nature? Section 1. Anatomy of a pattern. Let's quickly lay down the basic building blocks for our investigation. Okay, first up, we really need to understand what mathematicians mean when they say an asymmetric object. In math terms, an object is asymmetric if its only inherent symmetry is the identity symmetry. Now I know that sounds super formal, but it literally just means leaving it alone. If you can't flip it, you can't rotate it, and you can't mirror it to make it look exactly the same as it did before, well, then it's perfectly asymmetric. To keep things fun, we are going to use a little cartoon vulture as our mental model for a perfectly asymmetric object. Next, we need the mathematical engine that's going to actually drive our pattern, and that is called the Frieze group. Basically, a Frieze group is a concept for patterns that have one specific type of translation symmetry, and they just infinitely repeat along a fixed, one-dimensional line, kind of like a decorative border running along the top of a wall. Mathematicians have actually proven that in a two-dimensional plane, there are exactly 7, and literally only 7, types of these Frieze groups. We call them F1 through F7. Today, we're going to test what happens when we apply these exact mathematical groups to our objects. Section 2, the vulture experiments. Time to actually put our symmetry to the test. All right, meet our subject, the yellow-beaked vulture. This is just a randomly chosen, highly asymmetric design. Notice how there is absolutely no way to fold this vulture in half and have it match up perfectly, right? It is our pure asymmetric baseline. Let's start simple. We're going to apply the most basic Frieze group, which is F1, to our vulture. Group F1 consists exclusively of basic translation symmetries. That just means sliding the object along a fixed vector. So, when we slide our yellow-beaked friend to the right over and over, we predictably get this repeating Frieze pattern. And because we use the F1 group to create it, the resulting pattern logically belongs to Frieze group F1. It matches perfectly. Makes sense, right? Okay, let's level up a bit. What if we apply Frieze group F2? Now, F2 has translations, sure, but it also throws in something called glide reflections. This is where you slide the object forward and then reflect it across a horizontal line. Think of it exactly like footprints in the sand. When we apply these F2 rules to our asymmetrical vulture, we get these alternating red-beaked and yellow-beaked vultures. And once again, the resulting pattern perfectly matches the F2 group we applied. So it really seems like we found a solid mathematical rule. But you know there's a catch. Here is the million-dollar question for you. Does this always happen? Like when we apply a specific Frieze group to an object in a plane, are we absolutely guaranteed to get a Frieze pattern that matches that exact same group? Section 3. The rule-breaking double vulture. Enter the suspect that completely ruins our nice, neat hypothesis. I want you to compare our original, entirely asymmetric vulture to our new suspect right next to it, the double vulture. Look closely at this one. Unlike our first subject, it is definitely not asymmetric. It actually has a pre-existing reflection symmetry built right into it. You could draw a horizontal line right between those two beaks, fold it over, and boom, it matches up perfectly. And this is exactly where the trouble begins. Let's run our very first experiment all over again. We're going to apply that simple F1 group, just basic translation, sliding forward, to our new double vulture. But look at the result. Even though we literally only applied the simple F1 sliding rule, that inherent reflection that was already inside the double vulture completely hijacked the pattern. It forced it to feature glide reflections. So by applying F1, we accidentally created a much more complex F2 pattern. Crazy, right? So our assumed rule is officially broken. And this is a big deal because it challenges what mathematicians call the stability conjecture.
That's the assumption that a pattern's underlying rule stays stable and predictable. But because our double vulture wasn't completely asymmetric, because it essentially brought its own symmetry to the party, it fundamentally changed the outcome. It upgraded the final pattern to a higher-order Frieze group. So mathematicians are forced to drastically revise their hypothesis.
Section 4. Testing the revised conjecture. It's time to stress test these new rules. To do this properly, we need a brand new subject. We are going way back to basics with a completely random, highly asymmetric shape. Notice this jagged design, red interior, blue edges. There is zero hidden symmetry here. It's perfectly asymmetric. We're going to use this little guy for our ultimate test.
We aren't just going to slide this shape forward either. No, we are bringing out the big guns. We're going to apply Frieze group F7, which is literally the most complex of the 7 groups. This involves a massive, coordinated dance of geometry. We're reflecting the shape across vertical lines, translating it horizontally, rotating it 180 degrees around equidistant centers, and applying glide reflections that step forward in these really complex staggered intervals. It is just an intense interaction of multiple transformations happening all at exactly the same time.
And wow, here is the result. It looks incredibly complex, right? You've got these yellow, orange, pink, and light blue interiors overlapping and interacting all over the place. But here is the absolute magic of the math. Because our starting object was strictly asymmetric, this totally chaotic-looking final pattern successfully retains the exact F7 group identity we applied to it. It didn't accidentally upgrade to something else because it didn't have any hidden symmetry to mess with the formula. So the absolutely crucial takeaway here is this revised conjecture. Basically, if you apply a Frieze group, let's just call it phi, to a strictly asymmetric object in a plane, you will always, without fail, get a Frieze pattern that matches that exact same group phi. The asymmetry itself is the ultimate key to maintaining mathematical stability.
I actually want to pause on this quote from the source material because I think it just perfectly captures what we've been doing today. The main goal of pure mathematical research is to discover the truth, find valuable ideas, and imagine interesting objects. It is not to deduce or prove, and it is most certainly not to juggle numbers. Think about it. We didn't juggle a single number today. We literally just imagined shapes, applied logical rules to them, and watched the fascinating visual truth unfold.
But hey, mathematics is a continuous journey. We formulated a revised conjecture based on all the visual evidence we looked at today, but a true researcher's work is never fully done. So I'm going to pass the baton to you and leave you with this. Is this revised conjecture actually true, or is it false? Can you imagine the next rule-breaking shape that might come along and shatter this hypothesis too? Think about that the next time you look at a repeating pattern in the architecture of a bridge or the natural geometry of a seashell. Are you just seeing the simple rule or the hidden asymmetry behind it? Thank you so much for joining me on this explainer, and keep questioning the patterns around you.